This happens whenever the degree of the numerator is greater than the degree of the denominator. In such cases, divide the denominator into the numerator to write the expression in another form. We use synthetic division as shown. Here we are dividing x minus 2 into x squared plus 1. So we'll need a placeholder for x. So in the middle we have a 0. Since we're dividing by x minus 2, we'll put a 2 out in the front when we use synthetic division. And we'll drop in the 1. 1 times 2 is 2. 0 plus 2 is 2. 2 times 2 is 4. And 1 plus 4 is 5. So this gives us a remainder of 5. Recall when using synthetic division, it's always 1 degree less than the polynomial. So we have f of x can be written as x plus 2 plus a remainder 5 divided by x minus 2. So this is our function f of x after we divide by x minus 2. For very large values of absolute value of x, 5 over x minus 2 is close to 0. So the remainder approaches 0 as we get larger and larger values of x, so we can ignore it. And the graph approaches the line y equals x plus 2. This is an oblique asymptote, slanted, neither vertical nor horizontal for the graph of the function. A comprehensive graph of a rational function will show the following characteristics: all x and y intercepts, all asymptotes vertical, horizontal, and or oblique, the point at which the graph intersects its non-vertical asymptote, if there is any such point, the behavior of the function on each domain interval determined by the vertical asymptotes and the x-intercepts. Let f of x be equal to p of x divided by q of x. Define a function where p of x and q of x are polynomials and the rational expression is written in those terms. To sketch its graph, follow these steps. Step 1. Find any vertical asymptotes. Step 2. Find any horizontal or oblique asymptotes. Step 3. Find the y-intercept by evaluating f of 0. Step 4. Plot the x-intercepts, if any, by solving the equation f of x equals 0. These will be the zeros of the numerator, p of x. Step 5. Determine whether the graph will intersect its non-vertical asymptote, y equals b, or y equals mx plus b by solving f of x equals b or f of x equals mx plus b. Step 6. Plot selected points as necessary. Choose an x value in each domain interval determined by the vertical asymptotes and the x-intercepts. Step 7. We can finally complete the sketch. Example 5. We want to graph f of x equals x plus 1 divided by 2x squared plus 5x minus 3. I know there are a lot of steps, but we'll take it slow. We'll start step 1. Step 1, we're going to set the denominator equal to 0 and solve for our vertical asymptotes. We'll set 2x squared plus 5x minus 3 equal to 0, and we'll solve for our vertical asymptotes. So let's use the AC method. We have negative 6 on top and 5 on the bottom. The two numbers that multiply to get negative 6 but add up to 5 are negative 1 and 6. So we'll divide both of these by 2x. And I have negative 1 over 2x here, and this reduces to 3 over x. Using the bottoms up technique, I have this is equivalent to 2x minus 1 times x plus 3, and that's equal to 0. I can solve each one of these by setting them equal to 0, so 2x minus 1 equals 0, or x plus 3 equals 0. I can add the 1 to both sides, and we have 2x equals 1, or x equals 1/2, and here I could subtract 3 to both sides, and x equals negative 3. So we have two vertical asymptotes, one at x equals 1/2, and one at x equals negative 3. Two vertical asymptotes. Step 2, I want to see if there's any horizontal asymptotes, and for that I can look at the degree. Now, if you notice in the denominator, the degree is 1 more than the numerator. So as x gets larger, the denominator will grow faster than the numerator. And as a result, we have a horizontal asymptote. The horizontal asymptote is going to be the equation y equals 0. This is similar to our example from earlier. This is similar to example 4, where we had a horizontal asymptote of y equals 0. Step 3, we're going to look at the y-intercept. And for that, I'm going to substitute a 0 for the x value. So f of 0 equals 0 plus 1 divided by 2 times 0 squared plus 5 times 0 minus 3. This simplifies to negative 1/3. So we know our y-intercept is the point 0, negative 1/3. In step 4, we're going to look at the x-intercept. To do this, we're going to let y be equal 0 like before. So 0 equals x plus 1 divided by 2x squared plus 5x minus 3. Notice the denominator doesn't matter because we can multiply the denominator to both sides and it will cancel out. So all we need to do is solve 0 equals x plus 1. And we have that x must be equal to negative 1. So our x-intercept is negative 1, 0. This is our x-intercept, negative 1, 0. In step 5, I want to determine if the graph touches the horizontal asymptote. Recall the horizontal asymptote is y equals 0, so I'm going to let my function f of x be equal to 0. X plus 1 divided by 2x squared plus 5x minus 3, and we're going to set that equal to 0. If we multiply both sides by the denominator, it will cancel out the denominator, so we have just x plus 1 equals 0. And if I solve for x, I have x equals negative 1. So I know my graph intersects the horizontal asymptote at negative 1, 0. So this is the point where our graph intersects our horizontal asymptote y equals 0, which is the same as the x-axis. In step 6, I want to plot a point in each of the intervals determined by the x-intercepts and the vertical asymptotes to get an idea of how the graph behaves at each interval. In step 6, we're going to have to use a table to find where the graph is above or below certain critical values. I know we have a horizontal asymptote at y equals 0. We have vertical asymptotes at x equals negative 3. We have a vertical asymptote at x equals 1/2. We know there is an x-intercept at negative 1, 0. And we know there's a y-intercept at 0, negative 1/3. So now we have several regions we need to test in step 6. I want to look at the region to the left of negative 3, between negative 3 and negative 1, and negative 1 and 1/2, and to the right of 1/2. So we'll make a table of values between those regions and see if the graph is above or below, positive or negative. Here's step 6. From negative infinity to negative 3, I select the test point negative 4, plug it into the function f of x, and we get negative 1/3, which is negative. That implies it's below the x-axis. From negative 3 to negative 1, I pick negative 2, and I get 1/5 as the outcome. Since this is positive, it's going to be above the x-axis. From negative 1 to 1/2, I pick 0, an easy value to test. We get negative 1/3. Since it's negative, it's below the x-axis. From between 1/2 to infinity, I pick the test point 2, and f of x gives us 1/5. Since this is positive, it is above the x-axis. In step 7, we're going to complete the graph by sketching the function, and I always start with the vertical asymptotes first. Start with the vertical asymptotes, put it at x equals -3 and x equals 1/2. From there, I plot the x-intercept, so we'll plot the point -1, 0, and then the y-intercept, the point 0, -1/3. After we graph our vertical and horizontal asymptotes and our y and x-intercepts, then we'll plug in our test points. Here we have the test point to -4, -1/3. Here we have the test point -2, 1/5. And here's the test point 2, 1/5. Now, since the graph is bounded by these vertical and horizontal asymptotes, the left side here approaches the horizontal asymptote from the bottom, since we knew it was below, and it approaches the vertical asymptote here towards the bottom. For the middle of the graph, we know the left side goes to positive infinity because it is above the x-intercept, and here it goes below the x-intercept because our value was negative afterwards. And on the right side of the graph, we know it was completely above, so it must approach the vertical asymptote here on the top and the horizontal asymptote here on the right. Step 1, we're going to find our vertical asymptotes first. To do that, we're going to set the denominator equal to 0, and x equals 3 is going to be our vertical asymptote. In this case, we only have one vertical asymptote, and that's x equals 3. Step 2, we're going to find our horizontal asymptotes. I can look at the degree. Since the degrees are the same, the horizontal asymptote is essentially the ratio of the leading coefficients. So we have y equals 2/1 is going to be our horizontal asymptote, or y equals 2. Y equals 2 is our horizontal asymptote. In step 3, I'm going to find the y-intercept, and I'll do that by letting x be equal to 0. So f of 0 equals 2 times 0 plus 1 divided by 0 minus 3. And this gives us f of 0 equals -1/3. So my y-intercept is 0, -1/3. This is our y-intercept, 0, -1/3. In step 4, I'm going to find the x-intercept. And for this, I'm going to let y be equal to 0. So 0 equals 2x plus 1 divided by x minus 3. And I don't care about the denominator because if I multiply it to both sides, it will cancel out. So 2x plus 1 equals 0 now. Subtract 1 to both sides. 2x equals -1. And so x equals -1/2. That means -1/2, 0 is our x-intercept. Step 5. I want to know if our horizontal asymptote is going to intersect our graph f of x. And that's the question we're going to do in step 5. So we're going to set 2x plus 1 over x minus 3, which is f of x, equal to our horizontal asymptote, which was 2. I could solve for x now. Let's multiply both sides by x minus 3. The x minus 3's cancel out. And we get 2x plus 1 is now equal to, we can distribute the 2x minus 6. Let's subtract 2x to both sides. and 1 equals negative 6. This is a contradiction. That means the horizontal asymptote does not intersect. Does not intersect f of x. Our horizontal asymptote does not intersect our function f of x. Step 6, I want to get some values so I know if it's above or below certain points on the graph. So I always start by sketching the regions. So I always start by sketching my vertical asymptote. I know there's a vertical asymptote at x equals 3. I know there's a horizontal asymptote at y equals 2. So always start by sketching your vertical and horizontal asymptotes. Then I will start and plot my x-intercept. I know there's an x-intercept at negative 1/2, 0, and I know there's a y-intercept at 0, negative 1/3. So I want to pick a value to the left side of negative 1/2 to figure out if it's above or below the x-axis here. And then I want to pick a value between negative 1/2 and 3 to see if it's above or below the x-axis here. And finally we'll pick to the right side of 3 to see if it's above or below the x-axis. So here's the points that we picked. We picked negative 4, and when we plug it into the function we get a value of 1. So we know the graph approaches the horizontal asymptote from the bottom, and it approaches the vertical asymptote here from the bottom. The next point we picked was 1, and the output was negative 3/2. Negative 3/2 was below the x-axis, so we know it curves down and goes below the x-axis here after the 0 and the y-intercept. After the 0 and the y-intercept. And finally we picked the point 6, and that was completely above the x-axis at this point here, 6, 13/3, and it approaches the vertical asymptote as it goes to the left and the horizontal asymptote as it goes to the right. But remember, it does not cross the horizontal asymptote,